Today, we're jumping into something quite specific, connecting abstract math calculus, actually, to, well, the forest floor.
Yeah, it's based on a source a listener sent in, which is great. It's a paper looking at forestry growth rates technology.
Right, and it really zeroes in on one thing, using differentiation and integration to figure out the growth rate of tree diameter over time.
hmm So our mission basically is to unpack how this paper shows that connection works in practice.
Okay, let's get into it then.
What really stands out, I think, is how this paper takes these math concepts, the ones you might just see in a textbook,
Uh-huh.
and applies them directly to a very real-world problem. Understanding and, well, managing how trees actually grow.
Right, because a tree getting wider, its diameter increasing, that doesn't happen all at once. It's slow, it's continuous.
Exactly, over years.
So understanding that growth rate of tree diameter over time
hmm
is literally about putting a number on how fast that trunk is widening, like right now or maybe over a whole season. The paper treats it as a dynamic thing.
And that's right where, according to the source, differentiation becomes really essential.
Wow.
If you have a model, like a function, that describes the diameter over time, let's call it diameter d versus time t,
Makes sense.
then differentiating it, finding dt, that gives you the instantaneous growth rate, how fast it's growing at that very moment.
So the speed of the growth right then.
Precisely. And the source stresses this lets foresters know exactly how fast a tree is adding girth, say, at a specific point in its life cycle, which is, super important for checking its health or predicting near-term changes.
So differentiation is like the speedometer reading for the tree. The paper did mention some models, logistic curves, Gompertz curves, where the growth rate isn't steady.
That's right. It changes.
Differentiation helps pinpoint when that growth might be speeding up or peaking or slowing down. The source said that's key for like management decisions, when to thin the forest, maybe when to harvest.
Exactly. And the source talks about how the data they collect out there, maybe using dendrometers, these tools that measure tiny diameter changes.
Or tree rings, maybe? Increment cores?
Yeah, or analyzing cores, that data helps build these mathematical functions in the first place. So if differentiation is the rate now,
Uh-huh.
integration lets you see the bigger picture. The paper explains that if you integrate that growth rate function over a time period, say from year 5 to year 15,
Oh, yeah.
you can calculate the total accumulated change in diameter during that whole time.
Ah, right. So differentiation is the slope, the rate right now.
Yeah.
But integration is like the total distance traveled, the area under the curve of that rate, giving you the total gain.
You got it. And the source really highlights how vital this is for long-term planning.
Right. You might use differentiation to check if a tree seems healthy today, growing fast, but you'd use integration to estimate how much bigger it'll be in, say, 10 years, which obviously impacts timber volume estimates, things like that.
Absolutely. The paper shows how integrating these growth rates over decades, 20 or 30 years, gives foresters actual concrete estimates of what the forest might look like, how much timber they might get.
So it turns abstract math into a real forecasting tool.
Pretty much. It connects that tiny instantaneous rate to the big picture, the overall growth outcome.
So, okay, let's pull this together. What does it all mean? We've taken calculus concepts, differentiation for the speed, and integration for the total gain,
Right.
and seen how this specific paper applies them directly to understanding tree diameter growth in forestry. It's not just theory. It's about calculating the tree's actual physical expansion.
And what's really fascinating, I think, is how this source just clearly demonstrates that these seemingly abstract math tools become really powerful practical instruments for measuring, for modeling, for understanding the natural world.
Yeah.
It kind of begs the question, doesn't it? Where else might the math you're learning, maybe even calculus, pop up in surprising practical ways you just haven't thought about yet?
Definitely something to chew on next time you're walking past a tree.